Hi, my name is Yanrui from University of Science and Technology, Beijing. I would like to discuss our paper on refining turbulence for SPH approach in fluid simulation. We propose a vorticity refinement solver for SPH fluid simulation to recover turbulence details dissipated during simulation. Our method can not only amplify existing vortices, but also capture additional turbulence. The solver is straightforward to implement and can be easily integrated into existing SPH methods. As one of the most popular Lagrangian approaches to simulate fluid in computer graphics, Smoothed Particle Hydrodynamics, or SPH, can approximate physical values of a certain position using a kernel function W. The kernel function smoothes physical values of neighboring fluid particles indexed with J inside the smoothing length of particle I. It is also capable of approximating the first and the second derivative of physical values by simply calculating those of the kernel functions. In theory, fluid motions in nature can be described by the Navier-Stokes equation. This equation describes that the rate of change of fluid velocity is largely related to the density, the pressure gradient of it, body forces like gravity, and also the viscosity due to the relative motion inside of it. By applying the SPH approach to the Navier-Stokes equation, computer can simulate motion of the fluid under space and time discretization. The state-of-the-art SPH approaches often apply advection-projection scheme to keep the incompressibility of the fluid. Between two time steps, the gravity and viscosity are first considered to alter the speed of each particle. This is called the advection step. Then, the pressure of them is implicitly derived to reach the constant density condition, which is the projection step. However, if we use this scheme to simulate an ideal non-viscous vortex, numerical dissipation would happen. Particles which represent the vortex have a linear velocity of Vn, the direction of which is tangential to the vortex circle. In the advection step, the vortex would expand without the constraint of incompressibility. Now the velocity of each particle can be split into two parts, the tangential part and normal part. In the projection step, the pressure force of each particle is derived implicitly to counteract the density deviation caused in the advection step, making the fluid field incompressible again. The latest SPH approaches, like divergence-free SPH, would also consider correcting the divergence of velocity field, in which way the normal part of the velocity field could be totally removed, leaving only tangential part after each time step. During the whole advection-projection process, a certain part of the kinetic energy is dissipated, which can be described as a dissipation of vorticity field of the fluid. This artifact greatly jeopardizes the effect of the whole simulation, and we'd like to address this issue with our method. Traditional SPH approach can be regarded as a certain set of computation to compute the velocity and position of each particle from time step n to n+1. Our method consists of two parts. In the first part, we compute the exact value of vorticity dissipated between two time steps. Then in the second part, this vorticity is used to adjust the velocity field in time step n+1 to eliminate the dissipation. We obtain the vorticity dissipation using velocity field before and after the SPH solver. Then the refined velocity field is used to influence the original one at each time step. We use the vorticity equation and stream function respectively in the two parts of our method. So our method wouldn't recover excessive energy nor cause a divergence deviation in the velocity field. Given that the numerical dissipation of vorticity occurs between time steps, an ideal non-dissipative rate of change of vorticity is required to analyze the exact vorticity loss in each time step. We achieve this through the vorticity equation, which equals to the curl of Navier-Stokes equation. Theta here represents vorticity field. To discretize this equation for moving particles, we applied the difference formulation of SPH to derive the curve of velocity for each particle. This could give us a more accurate result. We compute the gradient of velocity of each dimension for each particle separately, represented by the xyz here, using the difference gradient formulation of SPH. Then the dot products are applied between the vorticity of particle I and the gradient of velocity from three dimensions separately. For the computation of Laplacian in the equation, we apply the artificial form described here. The d in this equation represents the number of dimensions of the simulation. With these three parts being calculated, the dissipated vorticity of each particle between two time steps can be expressed explicitly. Inspired by Zhang's method, we express the relationship between the velocity and the vorticity using the string function psi. The velocity field can be expressed as the curl of string function, while the vorticity field equals to the negative Laplacian of it. Green's function provides a semi-analytical solution for the string function. The derivation from the string function to linear velocity can be solved using difference curve formulation, generalized by the Helmholtz decomposition. The string function is the vector potential of the velocity field, which can be defined as follows. The string function at position x is computed by integrating the curl of velocity at position y over three-dimensional space. We next discretize this equation to get the string function at the local position of the particle I. Vj here stands for the volume represented by the particle with index j. Ideally, Vj should be infinitely small and all particles in the simulation domain should be considered in the summation. However, to limit computational overhead and its adaptability to SPH, we only include neighboring particles within the smoothing radius. This is justified by the fact that the influence of neighbor particles shrinks with distance. With string function obtained for each particle, the refined velocity for the particles can be obtained. To further extend the flexibility of our method, we introduce an adjustment parameter alpha, with the default value of 1 representing the ideal vorticity refinement. Here is the algorithm overview of our method. We first derive the vorticity field before and after the SPH solver using velocity field. The ideal vorticity field is obtained with vorticity equation. Note that we use the notation tilde to distinguish the velocity and vorticity field before the refinement from being refined with our method at time step n+1. Then the dissipated vorticity is used to calculate the string function. In the end, the refined velocity field from string function is applied to adjust original velocity field. Next, we'll show some experiment results carried out with both traditional DF-SPH and our method. We'll also compare our method with the state-of-the-art turbulence refined method, micropolar SPH. All experiments are carried out with kinematic viscosity coefficient set as 0.05 and rest density as 1000 kilograms per cubic meter. One should also be noticed that we apply the artificial viscosity mentioned earlier in these slides, which could potentially make these simulations more vibrant than using XSPH method. In the first experiment, a propeller is half submerged into the water and rotates at 3 radians per second. This simulation shows how each method would behave when kinematic energy is constantly added into the system. We can observe that neither the complex flow nor strong turbulence effects are produced and preserved using SPH. Both our method and the MP method can enhance the turbulence ratio effect. In fact, the MP method can produce a stronger turbulence than ours when T is set to 0.3. So the MP method could take a better advantage of an open energy system. In the next experiment, we show how both methods would handle a closed energy system. A hemisphere obstacle is flushed with a fixed volume of fluid. This means only limited kinetic energy is involved in this scenario. Both methods can increase the turbulence performance, but our result is more pronounced than the MP's. What's more, our method could remain calm after the energy is totally dissipated due to the viscosity like the traditional SPH. But the MP solver tends to constantly generate excessive energy, making the fluid hard to restore calm again. This diagram shows the percentage of energy exceeding traditional SPH in this experiment along with time under various parameter settings. We can see the green line represents alpha equals 1 and the green one represents T equals 0.2. Our method not only managed to generate more energy than MP, but also succeeded in converging the energy by not producing more of it than SPH, as the system should be stabilized. This simulation shows a board collides with a breaking dam which only allows fluid to go through the so-created gap. Only few vortices can be seen using SPH. Water flushes through the gap and dissipates quickly without clear turbulence effects. Compared to SPH, our solver generates several realistic vortices around the board and corners. To show the effectiveness of our approach numerically, the vorticity magnitude of our particles is visualized. The comparison shows that our method can recover energy from numerical dissipation effectively, and is thus able to simulate more details. In this experiment, the trace left on the surface lasts longer in our method than with the MP method as we set alpha equals 1.2, which is a critical point for both sailing animation scenarios. After the steering process, the surface details could remain clear and sharp in our method while maintaining calm. Experimental results show that, compared to the classical and macropolar SPH method, our method is able to enhance turbulence effects more visibly. Furthermore, our method guarantees energy conservation even when using a large particle radius or a large time step. This means that our method is still robust even under extreme simulation conditions and can handle complex large-scale scenes, as demonstrated in our simulation scenarios. We have presented a particle-based turbulence refinement method that recovers lost velocity from the difference between the theoretical and the actual vorticity value. Our method can not only increase existing vortices significantly by recovering numerical dissipation, but also generates new turbulence at potentially different locations. The method is stable and easy to be applied to particle-based fluid simulation due to its nature of divergence-free. In the future, we aim to investigate merging our method with macrostructural models, since these methods show great potential for rough simulation conditions and also have a close relationship with viscosity. Thanks for watching.